All right, let's talk about something we all take for granted, the water from our tap. Today, we're going to follow the amazing and kind of invisible journey that water takes. A trip that starts way out in a river or deep underground, and believe it or not, ends with you just turning a handle in your kitchen. So, let's get right into it.
You turn on the faucet, fill a glass, and you just don't think about it, right? But that crystal clear water has been on a wild ride. It's gone through this incredible, high-tech process, all engineered specifically to keep us safe and healthy. So what actually happens on that journey?
Okay, so our water's journey pretty much starts in one of two places. First, you've got your surface water. Think rivers, lakes, all that stuff. It's just out there totally exposed to pollution, and its quality can swing wildly depending on the season or even just a big rainstorm. Then you have groundwater. This is the stuff we pull from deep underground aquifers. Now the cool thing is, it gets naturally filtered by all that soil, so it's usually clearer. But it tends to soak up a lot of minerals on its way down. So right from the get-go, you've got two very different sets of problems to solve.
So before you can even think about cleaning the water, you've got to know what you're fighting. It's like being a detective. And the tricky part? A lot of the biggest culprits, the real troublemakers, are totally invisible.
First up, we've got something called suspended solids. I like to think of them as tiny little hitchhikers. Little bits of clay, silt, plant stuff, all just floating around. They're exactly why river water looks so murky. And getting them out, that's hurdle number one.
Okay, so you can imagine it'd be impossible to count every single one of those particles, right? So engineers have a really smart shortcut. They measure something called turbidity. It's basically just a fancy word for how cloudy the water is. The cloudier it is, the higher the turbidity, and the more stuff we know we've got to get rid of. It's like a super quick, super important checkup for the water.
And here is why this is so critical. This isn't just about making the water look nice. Those tiny particles, they act like little bodyguards for the really dangerous stuff, like pathogens. Seriously, they can literally hide bacteria and viruses, shielding them from the chemicals we use to kill them later on. That makes that whole disinfection step way less effective. It's a huge deal.
And that brings us to our number one enemy, pathogens. We're talking about the nasty disease-causing stuff, bacteria, viruses, you name it, that can make people really, really sick. Now again, you can't test for every single type of pathogen out there, it's just not possible. So what do engineers do? They look for indicator organisms, a classic one being E. coli. If they find that, it's a huge red flag that the water's been contaminated and other, even nastier, bugs could be lurking in there.
So you've got cloudy water that's hiding dangerous germs. How in the world do you fight back? Well, it turns out people have been tackling this problem for, get this, thousands of years. And over time, we've perfected this amazing multi-step process that's a little bit of chemistry, a little bit of physics, and a whole lot of human ingenuity.
And check this out. Our quest for clean water is basically as old as civilization. I mean, we're talking ancient Egyptians using clay pots to let the gunk settle out. The Romans, they built settling basins right into their incredible aqueducts. But things really kicked into high gear in the 1800s. And then, 1902, adding chlorine to water. That wasn't just an improvement, it was an absolute revolution for public health. A total game changer.
Okay, so today, most plants that treat surface water use this really elegant four-step playbook to get rid of all those suspended solids. The whole idea is to take those tiny, floaty particles and make them clump together into something big and heavy enough to get rid of easily. Let's walk through it. Step 1 is coagulation. So here's the science bit, but it's cool. Most of those little dirt particles have a negative charge, which means they push each other away, kind of like the wrong ends of two magnets. That's why they just float there. So we add a chemical called a coagulant. Alum is a common one, which is full of positive charges. It's literally like flipping on a chemical magnet. It cancels out that negative charge, and suddenly the particles can start clumping together.
All right, after coagulation comes flocculation. Now, the water is moved into these huge basins where it's mixed, but super, super gently. You could think of it like a slow dance. This gentle stirring just encourages all those little sticky clumps to bump into each other and form these bigger, heavier clusters we call flocks. And the whole point is just to make them big and heavy so they'll sink right to the bottom.
So once those flocks sink to the bottom, that's called sedimentation, by the way, the water on top is much clearer, but it's not perfect yet. It moves on to the final polishing step, filtration. Now, there are two main ways to do this. You have rapid sand filtration, which is the workhorse in most modern plants. It basically just strains the water. But then you have slow sand filters, which are, well, they're just amazing.
They actually grow this thin, living layer of microbes on top. It's called a Schmutzdecke that literally eats the leftover impurities. How cool is that? It's like nature's own little cleanup crew.
Okay, so at this point, the water looks perfect. It's crystal clear. But, and this is a big but, clear does not mean safe. Not yet. We've gotten rid of the bodyguards, those particles that were shielding the germs. And now it's time for the single most important step in protecting all of us.
And I love this quote because it just nails the bigger picture here. It's not just about engineering, pipes and pumps and concrete. It's about the provision of safe, palatable, and ample public water supplies. It's about providing the absolute bedrock of a healthy society, safe water.
So this final critical safeguard is called disinfection. Now, it's important to know the goal here isn't to make the water totally sterile. That would be insanely hard and cost a fortune. The goal is to wipe out any leftover pathogens down to a level where they're just not a threat to our health. And for over 100 years, the champion of disinfection has been chlorine. Why? Well, for one, it's great at killing microbes, but its real superpower is something called residual. This is the genius part. A tiny, safe amount of chlorine stays in the water as it travels through all those miles of pipes to get to your house. It acts like a bodyguard for the water itself, protecting it from anything it might pick up along the way.
Of course, in engineering, nothing is ever that simple, is it? We've learned that chlorine, our hero, can sometimes react with any little bits of organic stuff left in the water. When that happens, it can create these things called disinfection byproducts, or DBPs. And some of those can be a health concern. So that's the tightrope that modern water engineers have to walk. Use enough chlorine to kill the bad guys, but not so much that you create too many of these other unwanted compounds. It's a really tricky balancing act.
And all of this complexity, it's led to a really big shift in how we approach water safety. We've realized it's not enough to just focus on what happens inside the four walls of the treatment plant. You have to look at the entire system, from the absolute beginning all the way to the very end. This modern approach is called a water safety plan. So the old way was kind of reactive, right? You test the water at the end, and if you found a problem, you'd fix it. A water safety plan is the total opposite. It's proactive. It means you look at every single step, from the river all the way to your faucet, and you figure out where things could possibly go wrong. Then you put controls in place to stop those problems before they ever start.
When you boil it all down, this whole philosophy is about one simple, powerful idea. Prevention is better than a cure. You identify the risks everywhere along the line, and you stop contamination before it can happen. That's how you guarantee that the water is safe day in and day out.
So that leaves us with one final, pretty important thought. We've just walked through this incredible feat of engineering that makes our water clean and safe, but think about this. The cleaner we can keep our water sources, our rivers and our lakes in the first place, the easier, the cheaper, and the more effective this entire process becomes. In a way, the journey of that water drop, it really starts with us.